Okay, welcome to section 4.1, modeling the electromechanical subsystem. This is a section of the book Real-Time Computing for Mechanical Engineers that I wrote with Garbini and Devine. I'm Dr. Piccone. MIT Press published it. Check out their website for it there. And our companion website is rtcbook.org. Modeling the electromechanical subsystem. Motors come in many varieties, but the most common are brushed DC, brushless DC, permanent magnet brushed DC or PMDC, wound stator DC, which could be shunt, series, or compound connected, stepper, and alternating current or AC in its many flavors. We will focus on the brushed DC motor and specifically the permanent magnet brushed DC motor, which is the type chosen for the target system due to its ubiquity and appropriateness for the application of position and velocity control. This common variety is a popular choice for many applications, and the modeling techniques required are relatively straightforward and transferable to other classes of DC motor, for instance, brushless DC motors. Two dynamic models of the motor as a lumped parameter electromechanical subsystem are developed in this section. The model depends on the type of ideal electrical source chosen as the input. There are two common ideal source models, the voltage source model and the current source model. An ideal voltage source provides a specified voltage regardless of the current and power required to maintain that voltage. An ideal current source, conversely, provides a specified current regardless of the voltage and power required to maintain that current. We will develop a model for each type of source. So a motor model for each type of source, a voltage source, and a current source. Lumped parameter models. Consider the diagram in the above figure here, which shows a circuit with an ideal voltage source Vs, a resistor R, an inductor L, and a transducing element M. So here's the circuit. Here's our Vs, voltage source, resistance, inductance, and the transducing element M. The source Vs models a voltage applied to the motor from the driving circuit. Rotor windings are modeled with a series resistor R and inductor L. So these model the windings of the motor. There aren't actually discrete resistor and inductor elements. They are modeling the windings. The transducing element M models the interaction of the electrical and mechanical parts of the motor. The current IM through and voltage Vm across the transducing element are related to the torque Tm and angular velocity omega m of the shaft. So we see on the mechanical side a shaft, and that's the torque and angular velocity of that shaft, or what we were describing with Tm and omega m. The mechanical side of the motor, the rotor, shaft, and bearings are modeled by two rotational lumped parameter elements, a mass moment of inertia J and a viscous damper B, diagrammatically represented as a bearing. Okay, so that's our voltage source system. The current source system diagram in figure 4.1b, so the lower figure, is identical to that of the voltage source model except that it has an ideal current source IS. We develop both models in this section. So they both show up quite a bit, so we're going to develop them in parallel, even though at the end of the day, for the T1A target system, we'll be using a current source model. Okay, we begin with the voltage source model. In this section, we derive a state space model and a transfer function model of the voltage source model shown in figure 4.1a, the voltage source diagram. Throughout this book, we refer to a variable associated with a particular element by using a subscript. For instance, the voltage and current of the resistor R are denoted V sub R and I sub R respectively. Similarly, the angular velocity and torque of the inertial element J are denoted as omega sub J and T sub J respectively. We also frequently suppress notation for the time dependence of each variable, so we'll often write omega J and leave off the fact that it's a function of time. Voltage source, state space, model, foundations, and elemental equations. The state, i.e., the minimal record of the past history needed to predict the future behavior, which is Kalman's definition of state, of each element in a lumped parameter model can be described by two variables called power flow variables. For electrical elements, we use voltage and current. For rotational mechanical elements, we use angular velocity and torque. An elemental equation relates these two variables for an element. The resistor and inductor are given their usual linear voltage current relationships, VR equals RIR and DIL dt equals 1 over L VL, respectively. Similarly, the inertia and damper elements are given linear angular velocity torque relationships. So the torque of the damper is proportional to the angular velocity of the damper with constant of proportionality B, the damping coefficient, and the time rate of change of the angular velocity of the moment of inertia is proportional to the torque on the inertial element with constant of proportionality 1 over J. The final element to consider is the energy transducing element, which requires two equations, one for the voltage angular velocity relationship and another for the current torque relationship. A single motor constant Km can be used in both, so the angular velocity on the mechanical side is equal to the voltage on the electrical side divided by the motor constant, and the torque on the mechanical side is equal to negative motor constant times the current through the electrical side of the motor. The specifications of a motor often list two constants, a torque constant and a back EMF constant. If these are expressed in consistent units, they are in fact equal, and a single constant, Km, is sufficient. The constraint equations of the system are those determined by the connections among elements. Here we should take care to use the sign assignment from figure 4.1. The circuit elements all share a single current, and therefore all can be expressed as IL, that is IL equals IR equals IM. It's a single loop. The loop equation is that the voltage around the loop must sum to 0, or that the source voltage equals VR plus VL plus VM. Similarly, on the mechanical side, if we assume, and we do, that the shaft is rigid, there is a single angular velocity, so the angular velocities, drops taken to be positive in the direction of the coordinate arrow, can all be expressed as omega j. That is, omega j equals omega b equals omega m. Everything on the mechanical side has a single angular velocity. Finally, the sum of the torques taken to be positive in the direction of the coordinate arrow, including the inertial torque, Tj, must equal 0. So we have Tm plus Tb plus Tj equals 0. Excellent. So equations 1 to 7 are an independent and complete set. From them, a second order linear state equation can be formed algebraically, where we have the time rate of change of the state vector, which is omega j IL, equals the A matrix, a 2 by 2 matrix, times the state vector, omega j IL again, plus a B matrix, a 2 by 1 matrix, times a U vector, the input vector, which is just the voltage source. Here we have defined X as the state vector and U as the input vector. We choose y to be the angular velocity of the load as the output vector because the angular velocity and position are of interest to us for control purposes. We want to know the angular velocity and position of the load. So we take omega j to be the output. The output equation then is y omega j equals the C matrix, just selects out omega j, our state variable, which is what we are interested in for our output, and zeroing out the input and the other state variable. Together, equations 8 and 9, so this equation and this equation, form a state space model for the motor. Okay, voltage source transfer function model. A linear state space model, like we just derived, with the conventional A, B, C, and D matrices, can be converted to a transfer function model by taking a Laplace transform. The input U, state X, and output Y vectors have Laplace transforms capital U of S, capital X of S, and capital Y of S, where S is a complex variable. Let the matrix transfer function H of S be defined by the relation Y of S equals H of S U of S. Solving the state space model equations for H of S yields equation 10 as the solution, expressed in terms of the A, B, C, and D state equation and output equation matrices, and the identity matrix I. Applying this to the state space model for equations 8 and 9, where the A, B, C, and D matrices were defined with under brackets, the motor transfer function is given here, and we have simplified this down into a notation that includes two parameters, omega n, the natural frequency, and zeta, the damping ratio. Omega j of S and Vs of S are the Laplace transforms of the angular velocity of the load, and Vs is the input voltage. The natural frequency omega n and damping ratio zeta are, in this expression, given by these two quantities in terms of the parameters of the system. The set of equations 11 and 12 is our transfer function model for the motor with a voltage source. A first order approximation can be developed for the voltage source model. When only concerned with the mechanical response of the system, it turns out that for most PMDC motors, the second order model can be easily reduced to a first order model. The eigenvalues or poles of the system are given here to be lambda 1 and lambda 2 in terms of the damping ratio zeta and the natural frequency omega n. Motors are often overdamped, zeta greater than 1, so that poles are real. This makes one faster than the other. Consider the ratio given here. We see that lambda 2 over lambda 1 only depends on zeta, sort of a complex relationship, but we can plot it in figure 4.2, and we see that figure up here in the upper right of the slide. A large ratio corresponds to the lambda 2 mode decaying faster than the lambda 1 mode. As a practical matter, a system with a ratio of 6 or more, which corresponds to zeta being 1.4 or greater, is a good candidate for the first order approximation. So we can pretty much treat systems with damping ratio greater than 1.4 as first order models if we only are concerned with the mechanical side of the system. Okay, so what does that look like in terms of the transfer function? We have this second order transfer function that we've started with, and we're going to derive this first order approximation. So we recognize 14 as the combination of two systems, one for each pole or mode. So one for lambda 1 and one for lambda 2. Letting the leading coefficient hi, little hi, absorb constants. If we ignore the faster mode, we'll end up with h1 times 1 over s minus lambda 1. So we're saying that the lambda 2 mode is the faster mode. If we divide the numerator and denominator here and factor out a factor of lambda 1 into h1, which gives us a new coefficient h2, we can write this as 1 over tau s plus 1, where the time constant tau is negative 1 over lambda 1, the dominant pole. Matching the DC gain, h2, with that of equation 14, our tau s plus 1 term has to multiply this coefficient. Okay, we essentially said this has to equal our h2. We call this the first order approximation of the voltage source motor model. According to figure 4.2, this first order approximation of the second order transfer function is applicable for damping ratios of zeta greater than 1.4. It's important to recognize, however, that at high frequencies, we won't have the same roll-off of the low-pass filter with a first order approximation. So in the frequency domain, we should be very careful with this approximation. The current source model. The lumped parameter model of a motor connected to a current source is shown in figure 4.1b, which is given again here. The inductor current is determined by the input Is, which yields a first order as opposed to second order with a voltage source state space model. The single state equation can be derived by successive substitution, beginning with the elemental equation. So we have the elemental equation for the mechanical load side, so the rotor inertia. We have the time rate of change of the angular velocity proportional to the torque, Newton's second law in the rotational frame. We have a torque balance saying that the torque applied to J is equal to the motor torque and the bearing damping torque summed up. Then we can assign values to the torques based on their elements. So the torque of the motor is proportional to the current using the constant of proportionality, the motor constant. And the torque of the damper is proportional to the angular velocity of the damper with constant of proportionality, the damping coefficient. Okay, finally we have the constraint equations, which say that the current through the motor is actually fully specified by the current source. Note that Is pumps current through R and L. So L, the inductor, is no longer an independent energy storage element. Instead, it is dependent on whatever Is is. So we can substitute in Is for Im and omega b, because we only have one angular velocity on the mechanical side, is equal to omega j, which is going to be our one state variable. So note that the electrical element equations were not required to derive this result. They didn't even enter into the equations once. So the state equation is simply given here. So here is our state model. We have the time rate of change of omega j, so dx dt, equals, here's our 1 by 1 A matrix, times our 1 vector, state vector x, which is just omega j, plus our B matrix, which is also a 1 by 1 matrix, times the U vector, which is just Is, our single input. The corresponding output equation, again taking omega j to be the output, the angular velocity of the load or the inertia of the rotor. The corresponding output equation is given here, where we just take omega j from x. So the current source model is much simpler, and that's the main reason why we prefer it. We prefer using a driver for a motor that is a current source or can easily be modeled as a current source, because modeling the motor dynamics is simpler this way. Okay, so we can also derive a transfer function model for the current source model, and in a similar way to what we did for the voltage source model, we can find the transfer function, which is the output omega j over the input Is, to be equal to this ratio of values in S, the Laplace complex variable. Here we have used tau to be j over b, We call that the time constant. We will call the model described in this section the current source model. So how do we decide between using the voltage source model, like we derived in the previous section, and the current source model, which we just derived here? The way to do this is to choose the one that best approximates the motor driver in the system. So we're going to be driving the motor with an amplifier, and if the amplifier behaves most like a voltage source, we should use the voltage source model. If that amplifier behaves more like a current source, we should use a current source model for the motor system. Okay, modeling the target electromechanical system. Having developed the motor models, it is now time to consider the modeling of the target electromechanical subsystem, which we originally introduced in section 0.1. The motor side of the current amplifier can be modeled by the source in the current source model that we've just introduced. The operation of amplifiers for driving motors will be considered in section 4.3 in some detail. The mechanical side of the motor, its rotor and bearings, can be modeled by the inertial and damping elements of the current source model that we just went through. The flywheel inertia can be lumped with that of the rotor to form a single inertia, J, the sum of the rotor and flywheel inertias. The current source motor model, developed in the previous section then, can be understood to also model most of the target electromechanical system, with the provision that the inertial element J is understood to model the combined inertia of the rotor and flywheel. We will refer to this as the current source electromechanical system model. For a system with an amplifier that behaves as a voltage source, a similar conclusion can be reached. This model is referred to as the voltage source electromechanical system model. We won't be doing that in the lab, but we could develop a system that had a voltage source amplifier. To maintain a broad view of the problems of driving motors and designing controllers for them, we will consider both models in this chapter and the following chapters, meaning we're going to develop things as if we had a voltage source model in some cases and a current source model in others, because we want to see how it would work in either case because they're both common. In the end, we'll end up applying the current source model to our lab system, however. The system parameters, for example, the inductance, the inertia, the motor constant, to be used in the models can be found in Appendix A on the companion website. Okay, so that is the introduction to modeling DC motors, and we've done it with a voltage source model and a current source model, developed state space models for both of them, and we're going to be using them later in this chapter. Okay, see you next time.